Okay, so we're on to day 2 of Unit 9. Like I said in yesterday's lesson, this unit's also going to be a short one. 4 days, review, and then the test. So we're on day 2 of those 4 days. We're going to be looking at permutations. Some of this will be similar to what we did yesterday, but we're going to give a name to it. Then other things will be new. One thing you will need if you're watching the video is you will need your Inspire calculator. I'm going to show y'all a couple of calculators. They're not really tricks, they're just how to do it on the calculator. So you'll need that handy. I'll walk through the steps on the screen, that way you can see it. If you're watching the video, you can pause, rewind, etc. if you didn't catch what I did on screen. So what is a permutation? Well, for one, it's our topic of today, but you probably want the definition. A permutation is an arrangement of objects in which order matters. So you can make different arrangements, but if order matters, then you have a permutation. So if we put Bob before Susie in the next order, then that means it's a totally new creation. If you change the order, you have a new creation. So I'm just going to make note of that. The factorial of a positive integer n is the product of the positive integers less than or equal to n. And we read this, we don't say n exclamation point or n. No, it's n factorial. I could read this. This is the technical definition that you see on the screen, n times n minus 1 and so on. The easiest way to understand it is to look at an example. So 5 factorial, that's 5 times 4 times 3 times 2 times 1, blast off. You multiply all those together, you'll get 120. 7 factorial, start counting backwards. 7 times 6 times 5 times 4 times 3 times 2 times 1. Multiply all those together, you get 5,040. Then 4 factorial. Start at 4 and then just count down. 4 times 3 times 2 times 1. Multiply those together and you get 24. Now, as you can imagine, like even just looking at the 7, you probably were getting tired by the time you got to writing the 3. Like, okay, really, good thing I only have 2 and 1 left because I don't want to sit here and write like 10 factorial. 10 times 9 times 8 times 7, and so on. So there's a way you can do this in your calculator. So if you have your Inspire, I'm not going to give you the numbers, I'm going to give you the words to look for because the menus could change if the calculator were updated, or maybe you have a different version because it's one that you bought, not one from the school. Who knows? But you go to menu, probability, and then factorial. Now, if it's the original one from the school, it'll match the screen that I'm about to show y'all here. So you would have to type your number in first. Let's say we were doing 7 factorial. Well, let's not do 7. We've already done 7 on the paper. Let's do 10 factorial. So you would type 10 in the calculator and then go to menu, probability, which is option 5, and then factorial, which is probably going to be option 1. So menu, probability, factorial. If it's the normal calculators, it would be menu 5-1. Again, that could change if you get an update. So that gives you the exclamation point. Hit enter. There's our answer. 3,628,800. Another way you could do this, if you didn't want to remember that, is you could hit 10 and then down on your keyboard beside the G, there's another button where you can do like a question mark, an exclamation point, etc. You could hit that and choose the exclamation point and then hit enter. Gives you the same answer. So 2 different methods to get to it, but you still get the same answer. So that's how you do factorials in the calculator. Okay, let's look at this first example. Student council members have selected 10 students to choose from to fill positions of president, vice president, secretary, and treasurer. Each student can only fill one position. How many different outcomes are possible? Well, how many offices are there to be filled? There's president, that's 1. Vice president is 2. Secretary is 3. Treasurer is 4. So let's draw 4 blanks down here because there's 4 different offices we're filling. 1, 2, 3, 4. Okay. Now let's say you were running for student council officer. Would it be different if you got president versus treasurer? Would that be a different outcome? Yes. President is different than treasurer. So what does that mean in the grand scheme of the problem? That means that order matters, which means we have a permutation. Okay, so we know order matters. Now, can you be both the president and the treasurer at the same time? Well, I mean, you could, it wouldn't be ideal. So since it's not ideal, we're going to say no. You can't be the president and the treasurer at the same time. You can only be one. So not only does order matter, you can't have more than one position. I mean, it even tells you that in the problem. Each student can only fill one position. It tells us that. So with that in mind, let's think about the president. So there's 10 students we can choose from. That means for president, there's 10 different options. So we name Bob the president. If Bob's the president, how many options are left to pick from for vice president? So we got 10 options for president. Well, Bob's out, so now there's only 9 people left. So now we're going to have Sue as your vice president. So now Bob and Sue have been chosen. How many people does that leave for secretary? There's 8 people left. So let's pick Billy Joe for secretary. So now Bob, Sue, and Billy Joe are out of the picture. How many does that leave for treasurer? 7. And just for the sake of it, let's say Bubba gets treasurer. So now, that was one outcome. How many total outcomes are there? Well, do 10 times 9 times 8 times 7. Multiply those together, they get you 5,040 different outcomes. If every outcome is equally likely, then we could find the theoretical probability. And simply put, that's the number of favorable outcomes so how many we want to happen over the number of total outcomes. So how many could happen? How many we want over how many could happen. Another way you could look at this is the part over the whole. So let's take this and look at some probabilities using a deck of playing cards. A standard deck of playing cards contains 52 cards. 13 of them are spades, which are black. 13 are hearts, which are red. 13 are clubs, which are black. And 13 are diamonds, which again are red. So the first one asks us, what's the probability of drawing a spade? Well, before we even get to that, let's name how many total cards. They tell us that there are 52 cards. This is our total. Or in the terms above, this is the whole. The whole deck has 52 cards in it. A asks us about drawing a spade. Well, how many spades are there? 13. So the probability would be 13 over 52. So how many we want? We want a spade, that's 13 of them over the whole. Now, when you do probabilities, you always want to reduce the fraction if that's what you're going to use as your final answer. 13 over 52 reduces to 1 over 4. Or you could also put it as a decimal. 1/4 is equal to 0.25 as a decimal. There's your answer. Next one, what's the probability of drawing a club or a diamond? How many clubs are there? There's 13. How many diamonds? Again, 13. So total, we have 26 that we want. So the probability would be 26. That's how many we want, over how many total? 52. 26 over 52 reduces to 1/2, or you could say 0.5. Now they ask us, what's the probability of drawing a red card? Well, which suits are red? And if you don't know, it tells you. Hearts are red, and there's 13 hearts. What else are red? Diamonds, and there's 13 of those. So together, how many cards do we want? 13 plus 13 is 26. So this example looks like the one we did just above. 26 divided by 52 reduces to 1/2, which is 0.5 as a decimal. And part D, and throw y'all a curveball. What's the probability of drawing a blank card? A blank card. That's not a typo. I didn't say black. I said a blank card. Are there any blank cards in the deck? Assuming the manufacturer did not make a mistake. No, it can't happen. There's no blank cards. So if it can't happen, that probability is equal to 0. Ain't gonna happen. If it did, I'd go get my money back. Okay, so there's that example. Now let's look at the next one. We're dealing with ID numbers. A student ID has 5 digits selected from 10 possible digits. The 10 they're picking from are just your normal numbers. 0, 1, 2, 3, all the way to 9. Those are your digits you're picking from. Assume digits cannot be repeated. So, that's good news. That means you can't have an ID number that's all 6s. You can't happen. Can't repeat digits. So this is kind of like what we did yesterday some, where I said you couldn't repeat something, so we had to count down. Well, how many digits are in a single number? A single ID number has 5 digits. Let's make 5 blanks. Okay, there's my 5 blanks. For the first digit, have I used any yet? No, so I can have all 10. So let's say a 2 is your first digit. Now, I've used 1, so how many are left? 9. Got my second digit, which means I've used 2. How many are left? 8. And then you just keep counting down. 7 and 6. So 9, or 10 times 9 times 8 times 7 times 6. This will give us 30,240 ID cards that you can make, or ID numbers that you could have. Now let's say the school district is just being really nice and they're going to draw one ID number and send them on a 7-day vacation to Fiji. Don't know where the money's coming from, but they found some. They're going to send a student with their family to Fiji. And so your ID number is 45362. Let's say that's your ID number. How many do you want? How many numbers do you want them to draw? Just yours, right? You don't want your friend going on the trip. You want to leave your friend here and you're the one going. See ya, wouldn't want to be ya. So you only want that number, your number, to be drawn. There's only one desirable outcome. Okay, well, the probability that your number gets drawn would be 1 over 30,240. That's the fraction. The decimal would be 0.00033, which, if you're wanting to know your chances of winning, that might not tell you much. So just for the heck of it, so you can understand your actual probability of winning, that means you have a 0.0033% chance of winning. In other words, it's not likely you're gonna win. But hey, at least the chance is there that you could. Okay, there's that example. Now let's actually talk about permutations. We just spent most of the time looking at factorials and kind of setting a stage for permutations that we're going to look at on the back. So the ordered arrangements of R, which is less than or equal to N objects selected without replacement, meaning we're not able to reuse it. From N distinct objects is the number of permutations of indistinct objects taken R at a time. So the formula for that is N factorial over N minus R factorial. On your calculator, you can go to menu, probability, which is more than likely option 5, and then permutation, which is more than likely option 2. For the calculator, though, for the syntax, which means the order you have to put things in, it's going to look like this. It's going to come up NPR with a parentheses, and then these blanks and commas won't be there. All you'll have is NPR and a set of parentheses. In this first blank, this one is where the number for N goes. How many total objects are you picking from? That's where N goes. The second blank is where your number for R goes. How many are you actually picking? So let's look back at examples 1 and this shouldn't say example 1 and 2. This should say example 1 and 3. Let me correct that right quick. This should say example 1 and example 3. Okay, example 1. How many students were we picking from for the student council example? We had 10 students to pick from. And how many offices were we filling? We had 4 positions to fill. So on your calculator, you could do NPR, so permutation, and do it to where the first blank, remember, is your N. So we pick 10. R is how many positions? There's 4 positions. Let's do that in the calculator. We go to menu, probability, permutations. So that's where it pops up with the NPR, but then you just have parentheses. So the first number you type is the 10. Then you have to put a comma. If you're not familiar with where the comma is, it's beside the O on the keyboard. So 10, comma, and then we're doing 4 positions. Hit enter, and it'll tell you 5,040. So 5,040 is your answer. What do you notice about this number? Whoa, who'd have thunk it? It's the same as what we got. So this is like, it's not really a shortcut, it's just how you can do it in the calculator. Now let's look back at example 3. I'm going to put it kind of at the top of the screen so you can see it. How many digits did we have to pick from? Well, so we picked 10 possible digits. How many distinct digits are chosen? Meaning we couldn't repeat them. Well, there's 5 digits that we picked for the ID number. So NPR, which one goes first? The 10. And then we have the 5. Let's do that in the calculator. So menu, probability, permutations. We put our 10 in there, do a comma, then the 5, hit enter. 30,240. There's our answer. And again, what do you know? It's the same as what we figured out in example 3. So yes, you can think them out, think through them like we did at first, or you could use the permutations and say, hey, wait a minute. Order matters because we're doing an ID number in this case, and we can't repeat digits. I'll just do it this way and not have to type in 10 times 9 times 8 times 7 times 6. This is way easier. But it's up to you. Either way, you'll get the same answer. So that's permutations where we don't have to deal with any sort of repeats. But that's not always reality. If we're drawing without replacement and order matters, we may run into cases where an object is repeated. When this happens, we take the total number of arrangements in factorial, but then we have to divide out the factorials of the repeats. This type of problem is typically called the Mississippi problem because of how many times each letter repeats in the spelling of the state. We've got 4 I's, 4 S's, and 2 P's. So let's say you're on a game show and they give you the following letters. They get and ask you to unscramble them to name a U.S. river. And you don't know about the Mississippi River for whatever reason. It's the only one with 4 S's, 4 I's, and 2 P's, but you don't know that. Maybe you fell asleep in geography or history when they talked about Mississippi. I don't know. But they give you this random spelling and you have to rearrange them. Now, just to illustrate my point, let's say you have this first rearrangement. Let's say that's one rearrangement. And then we're going to have another here. If I wouldn't have changed and made it look like, oh wait, he switched the 2 I's because I have one I that's red. What would you think about these 2 arrangements? Would they be any different? If it was all written in black, would you be able to tell the difference? No. So without color, these are the same arrangement. So that means they're not unique. And if we're talking about arranging something, you want it to be unique. So that leads to where that tells us, okay, we've got to figure out what are all the repeats. What all repeats when you spell Mississippi? Well, how many I's do we have? There's going to be 4 I's. What about S's? 4 S's. And how many P's? There's 2 P's. The total letters in Mississippi, well, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 total letters. Using our little formula up above, to get the unique rearrangements, we'd have to do 11 factorial divided by 4 factorial times 4 factorial times 2 factorial. Let's do this in the calculator so you can see how I do it. That way you won't make some of the common mistakes. Okay, I'm going to do it without doing control divide. Well, actually, I'll do it both ways. So control divide. On top, we need 11 factorial. So we cannot use NPR. Even though this is a permutation, you can't use NPR. Ain't going to happen. I mean, you could, then I'd count it wrong, and then you'd be sad. Let's not be sad. So we have to do 11 factorial on top. So menu, probability, factorial. On the bottom, we need 4 factorial times 4 factorial times 2 factorial. Notice I did the bottom, I got the factorial in a different way because it's quicker. There's 2 less button pushes doing it this way than the menu probability factorial. Okay, so we do it. Our answer is 34,650. Now let's say you didn't do control divide. Let's just say you did 11 and then factorial. And you just hit normal divide. If you did that, you would have to put the bottom in parentheses. If you don't, it'll just do 11 factorial divided by 4 factorial. So I'm going to do it without the parentheses first to show you how it will give you the wrong answer. You have to put parentheses. Does that match what we just did above? For one, the answers don't match, and two, you can look and see that it did 11 factorial divided by 4 factorial, but then that's the only thing it divided. It multiplied the other 4 factorial and the 2 factorial and made our answer bigger. You have to put parentheses on the bottom. Let's do it the right way. Factorial divided by, then I open the parentheses and do the 4 factorial, 4 factorial, and 2 factorial. Hit enter. Boom, gave us the right answer. Make sure you put your parentheses. So 34,650 is the answer. That's how many unique ways there are to arrange Mississippi. But they didn't stop there on the question. It didn't say how many unique ways. It asked what's the probability that you can do this randomly. So probability, there's only one way to spell Mississippi. So our probability is 1 over 34,650. Or as a decimal, it'd be approximately 0.0000029. Pretty slim chance of you doing it randomly. Okay, so there's the notes. Stay tuned for the guided practice.